2.2, the limit of a function. After explaining to a student through various lessons and examples that the limit as x approaches 8 of 1 over x minus 8 equals infinity, I tried to check if she really understood that, so I gave her a different example. This was the result. That's your bit of humor for today.
Let's start off looking at the function defined by f of x equals x squared minus x plus 2 for values of x near 2. Now we're going to write that symbolically as the limit as x approaches 2 of x squared minus x plus 2. And that's shorthand for writing all of that. So in order to do this, we're going to start by looking at the graph. And what we mean by the limit as x approaches 2 is what value does the function approach as x gets close to 2 from both sides. And we're going to talk about the importance of that from both sides a lot in this section. So what we do is we graph the function x squared minus x plus 2, and then we look as x approaches 2 from both sides. What does the function approach? What value? Whenever we say value, that means y value. So we can either look at the graph here, we can look at a table of values, and as I said, we need to look from both sides. So we need to look from the left side, okay, as x gets closer to 2 from the left side, value smaller, and from the right side as x gets closer to 2 from the right side, from larger values. And we'll see that from both sides we get very close to 4.
So I did just want to step you through how to do this on your calculator. So if you put in your y1, if you put in this function, x squared minus x plus 2, and then you go ahead and you go to your table set, because we need to set that up first. So second window will bring you to your table set. And since we're looking for the limit as x approaches 2, we want to start a little bit to the left, and I'm just going to start at 1.997. So 1.997, and this delta table means, you know, the step between my x values that I have, so I'm going to make that pretty small. I like to, by default, just think of 0.001. That's pretty safe. And then leave it as auto, and then to get to the table, you do second table, which is on top of your graph button. And so you can see here that from both sides, from both the left and from the right, I'm getting close to a value of 4. And in this example here, my value at 2 is actually 4 also. So that's how you do it on your calculator.
So we can write the limit as x approaches 2 of x squared minus x plus 2 equals 4. Now let's look at the definition. We say that the limit as x approaches a of f of x equals L if we can make the values of f of x close to L as x gets really close to a. Note, the function does not need to be defined at x equals a. We haven't seen an example of that yet, but we're about to in the next slide. Also, remember, we must look as x approaches a from both the left and the right. And I can't emphasize that both enough. Now let's look at some figures. If we look at figure A, that's our most obvious example, seeing that the limit as x approaches f of x equals L. Because we see that from both the left and from the right, we're getting close to the value L. In fact, in A, we actually see that f of A is equal to L. So we see that the limit equals L and f of A equals L in figure A. In figure B, we see again that from both the left and the right side, we're getting close to the value L. However, what is f of A in this case? It's some value let's call it K here. Right? So in figure B, we see that the limit does not equal the value at that point. That's going to be important. And in figure C, we see that f of a does not exist at all, and we can abbreviate that DNE. F of a does not exist. Now let's look at another example. The limit as x approaches 1 of x minus 1 over x squared minus 1. What do you know about this? Well, we know that the denominator can't be 0, so where is this function not defined? This function is not defined at x equals 1, right? So let's look at a graph of this for a second. And we see, again, remember the importance that when we want to look at the limit as x approaches 1, we need to look from both the left and from the right. And we see here that from both the left and the right, if we look at the graph, it's approaching 0.5, and we're probably going to want to look at a table of values.
So now how would I do this one on my calculator? In my y1, I would go ahead and put in my equation. So parenthesis, x minus 1 all over x squared minus 1. And then go ahead and go to your table set again, so second table set. And I'm looking at values near 1, so a little bit less than 1 would be 0.997. And again, I like to keep my delta table at 0.001 for these problems. And then just go to second table, and so you can see from both the left and from the right, I'm getting close to 0.5, even though at 1 my function is undefined, so my limit would be 0.5.
Let's look at another example. Let's find the limit as t approaches 0. Okay, we have a t here in our calculator. We're going to put it in as an x. No big deal. Let's go ahead and put it into our graphing calculator. And y1, we'll put this equation, the square root of x squared plus 9 minus 3 all over x squared. And we want to look as the x value gets really close to 0. We have really tiny values. We have a really tiny step here, and in this picture, in this table here, we have a little bit of a larger step, and we see that we arrive at different answers. Now, which one is correct? Now, I think it's a lot easier to look at it graphically here, and this is going to be really important, especially on the AP exam. They do tend to put in 1 or 2 multiple choice questions where your calculator lies to you. And so here we can see what that means. We can see that if we zoom in, to this window in part A, we see this graph. If we zoom in a little more, it looks pretty linear. If we zoom in a lot, we see this crazy stuff happening. And part D, we zoom in really, really far. So what's happening? Well, what happens is when we get to values that are too tiny, our calculator starts making some rounding errors, and it makes us go a little crazy. So we want to zoom in enough, but not too much. So part A and B is good. We don't want to zoom in too much. We don't want to make our step go way too tiny. So something like 0.001, 0.01 is a good step to go by in general. But you just have to be careful of that, and we'll be talking a lot more about that as we go on. Our actual correct answer in this case is this. So our limit as t approaches 0 is about 0.166. Let's talk a little bit about one-sided limits. I told you before, in order for the limit to exist, we needed to look from both the left and the right. But we do have one-sided limits. We can just look at the limit from the left or just the limit from the right. Now, in order for the limit to exist, the limit from the left and the limit to the right have to be the same. Okay? So now let's just look at the left-hand limit. The left-hand limit we can write as the limit as x approaches a from the left. This little minus sign means from the left. Okay? And so that's saying what value does it approach from the left-hand side, as in figure A. Figure B, we look at the limit as x approaches a from the right. That little plus sign indicates that we're talking about from the right. So that's saying from the right, what value are we approaching? And so in order to have a limit exist, the limit as x approaches a of f of x to equal L, that only happens if and only if the limit from the left equals L and the limit from the right equals L. So let's try and show that the limit as x approaches 0 of the absolute value of x equals 0. How are we going to do this? Well, let's first think of the piecewise definition of the absolute value of x. So if you remember what piecewise means, we want the absolute value of x. What does it equal? Well, it's going to be x for all values greater than or equal to 0. Right? If x is positive, then the absolute value of x is just x itself. But if x is less than 0, then it's going to be the opposite of x, right? Because the absolute value of -5 is 5, for example. So let's look at the limit. We want to look at the limit as x approaches 0 from the left, and we want to look at the limit as x approaches 0 from the right. In order for the limit as x approaches 0 of the absolute value of x to equal 0, we've got to have it equal the same thing from both the left and the right. Right? So we just said. So in order to do this first, evaluate this first limit from the left, we're going to use which one? We're going to use if x is less than 0. We're going to use this equation, right? And so we can stick 0 in. And so that just equals 0. And from the right side, from larger values than 0, we're going to use this definition, just straight old x. And since we're at 0, it equals 0. Therefore, since the limit from the left equals the limit from the right, which equals 0, we can say that the limit as x approaches 0 of the absolute value of x equals 0 also. Done. Now let's try and prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So let's go ahead and look at our piecewise definition again of the absolute value of x. Let's just write it there for reference. Okay, so now let's again look at the limit from the left and from the right. Okay, so the limit as x approaches 0 from the left of the absolute value of x over x is going to be from the left. We use the smaller values. Is going to be the limit. The same thing as negative x over, right, because we're using negative x over x, which is -1, right? Let's go ahead and do it from the other side. From values that are greater than 0, we're going to use this definition. The left and the right are not equal. Therefore, since the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. We can say that the limit as x approaches 0 of the absolute value of x over x does not exist. DNE for short is fine. All right, now let's just graphically look at some of these things. So, what is the limit as x approaches 2 from the left of g of x? We have y equals g of x graphed here. So, from the left, we are approaching the value 3. Remember, it does not matter that in this case, f of 2 is not defined. That doesn't matter here. What is the limit as x approaches 2 from the right? From the right-hand side, as we get close to 2, we're getting close to the value 1. So what is the limit as x approaches 2? Well, since the left limit does not equal the right limit, we say this does not exist. Now let's look at the limit as x approaches 5 from the left. So now we're looking as x approaches 5 from the left. We are getting close to 2, right? What about from the right? We're still getting close to 2. So what is the limit as x approaches 5? Well, that's what it is from the left and the right. From both the left and the right, in both D and in E, we're getting close to 2. Do not confuse that with f of 5, because what is f of 5 in this case? What is the value when x equals 5? So note, the limit does not have to equal the function value at that point. And that's it for this lesson.
Okay, let's close with this example here. Sketch the graph of an example of a function f that satisfies all the given conditions. So the first thing, it says that the limit as x approaches 0 of f of x equals 1. So I don't know what's happening at 0, but I know since it says the limit as x approaches 0, it must be from the left and from the right. So I'm getting close to a y value of 1 at x is 0. So I'm going to put an open circle because I don't yet know what's happening there. And I'm going to put a left tail because I know it's happening from the left, and a right tail because I know it's also happening from the right. Now, as x approaches 3 from the left, so that's 1, 2, 3, my y is approaching -2. So that's right here. Again, I'm going to put an open circle there, but I'm just going to put a left tail because this is only happening from the left-hand side here. And actually, from the right-hand side, it's approaching 2. So x value of 3, y value of 2, and from the right-hand side, it's approaching 2. So I'm going to put a right tail on it. And then it actually tells me that f of 0 is -1. So f of 0 is -1. That's going to be my closed circle. And f of 3 is 1. F of 3 is 1. So that's going to be where my closed circle is. Now, I've kind of got to just play a game of connect the dots. So this could go anywhere. I'm just going to choose to put it down. Now, these have to touch. So I'm going to make them touch in the easiest way I can. And then this tail, it could have gone down, but I'm just going to choose to let it go up like that. Just make sure at the end of the day that what you've drawn is a function. And that's it for this lesson. Hope you enjoyed.